All right, welcome everyone. Welcome back to our final meeting of the Water, Wetlands and Watershed Seminar for spring 2025. Thanks for joining us all semester and our final speaker today. I need to give you co-host permissions there. Jaime, let me do that right now. You are now co-host and you should be able to share. So our presenter today is Dr. Jaime Bayabil, and Dr. Bayabil is an associate professor of water resources in the Department of Ag and Bioengineering. And he is down in Homestead, Florida, in the Tropical Research and Education Center down there. So Dr. Bayabil's research focuses on understanding soil hydrologic dynamics at multiple scales by leveraging emerging technologies, model simulations, and machine learning tools. Basically looking at how to improve soil and water management in mostly agricultural settings, and also boosting agricultural productivity along the way. So he's got a lot of publications, a lot of sort of scholarly outputs, but I think some of the most sort of telling attributes of his CV is that he's got a fair number of really nice awards, including the 2024 University of Florida Water Institute Early Career Faculty Fellowship, the 2020 Outstanding Young Researcher Award, and the 2021 Outstanding Young Extension Worker Award from the American Society of Ag and Biological Engineering. So the question is, like, when do you get to stop applying for the young and early career awards? And then you get some more gray hair and you can apply for the next round. But Jaime, it's great to have you in class today, and the floor is yours.
Thank you, David. I think I already shared my screen, right? And let me know if you see my slides.
That's perfect. Perfect.
Full screen, right? Yeah. Thank you, David, again for the opportunity to talk to you today. My name is Jaime North, but to make everybody's life and for everyone to remember me, I go by Jaime. So today I'll talk about some of our work on improving agricultural water management, specifically in calcareous soils with a shallow aquifer system that we have here in South Florida. Briefly about my research group, it's what's called the Water Resources Research Group. We focus on developing data-driven soil and water-based management practices with the goal primarily to conserve water, freshwater resources, but also we expect that will have added benefits in terms of protecting water quality, improving agricultural productivity, soil health, and in general, sustainable use of freshwater natural resources. So we do research at different scales, from column scale in the greenhouse, plot studies, watershed simulations. We employ different kind of tools, UAV systems with multispec and thermal and other kind of sensors, Internet of Things. We collect literally a lot of data, in fact, and we are having difficulty in handling, storing, and processing that data. And recently, I started hiring computer science to help with that. And we recently started working on different kind of data analytics, machine learning models, of course. Uh, uh, Hydrologic and crop simulation models are some of the tools we use to extract useful information that could be actionable and implemented at different stages. So my position is located at the Tropical Research and Education Center, and I have a two-way split. 40% of my employment requires doing research, and 40% of my employment is doing extension, which is translating the research that I do and other scientists do, so that it could be implemented by stakeholders, mostly growers in my case. A little bit of background information about South Florida soil and hydrology. I don't know how many of you are aware of this, but we have a very unique soil. It's called chrome soil. It has more than 50% gravel. As you can see in the left side from the picture, it's been created by breaking the limestone using heavy-duty machines. And this soil has some unique properties. It has high pH, high calcium carbonate content, low water holding capacity, low nutrient retention, and yet it's very productive, and it's widely used for vegetable production and also some tropical fruit trees as well. So between this shallow soil, which is usually between 6 to 8 inch deep, and the shallow aquifer system, the Biscayne aquifer that covers more than 4,000 square miles, and provides as a freshwater source for multiple counties in South Florida. There is a limestone bedrock. The limestone is also highly permeable, so you can imagine like the surface and groundwater are always hydrologically connected, and when you have a big storm event or after hurricane events, flooding, salinity is a big issue. And it's not that uncommon to see fields completely flooded for several days after big storm events because of the groundwater level being very shallow and sometimes trees to the surface, and the topography is flat and water has nowhere to go except. In the projection from NOAA in 2022, there was a joint report by NOAA and several other agencies that look into sea level rise scenarios in the future. And it's not that it doesn't look good for Florida in particular, and mostly coastal cities in the East Coast and including the Gulf. And their estimate is that by 2050, the average sea level rise will be about 30 centimeters, um, and the flooding will be like 10 times more often as we are currently seeing. And this is even bad news, right? Um, so with that, we did some modeling work looking into what sea level rise scenarios in the ocean mean to groundwater level and groundwater quality inland, using NOAA's different sea level scenarios. Here, we selected two sea level rise scenarios, intermediate and high, which correspond to, if you are aware of the climate change scenarios, the RCPs, in the past and now the SSPs. The intermediate corresponds to SSP 4.5, which means there would be some um, effort in mitigating climate change emissions, and some mitigation efforts will reduce the result in a reduction in sea level rise. The high sea level rise scenario represents the worst case scenario, which is SSP 8.5, which means business as usual, no mitigation effort. And as you can see, for the different periods, this sea level rise scenario range between zero point 0.4 to 2.2 meters, and the three periods range from 1985 all the way to 2100. And we plugged in these scenarios to a model, which I will talk about in the next slide. And we were interested to see how that would affect groundwater level and water quality. So our study area was obviously Miami-Dade County in South Florida. In that study, we incorporated data from 122 ground well monitoring stations, and we used the East Coast surficial model. It's a modified version of the CWAT model that was done by South Florida Water Management District. Um, in fact, we just published this paper recently on our systems and environment. So the model this is a model efficiency in terms of simulating groundwater level and total dissolved solid. As you can see, it did a better job in simulating groundwater level compared to TDS in this case. R square range between 0.5 to 1 for groundwater level. For TDS at some wells, the R square value was lower than 0.5. So after that, what we looked was projected groundwater level under different land use scenarios. Here, let's say a summary of the results for under the worst case scenario for the three periods. How groundwater level will change in ag, urban, and wetland. Ag and urban, the projection shows that up to 2.5 meter increase, but the projection for wetland was slightly higher than in ag and urban areas. And we can see on the right side the spatial coverage of this rising sea level rise scenario. And as you can see, the darker blue colors represent the end of the century to around 2100. Worst case scenario where you have more groundwater level increase in wetland areas. This covers the Everglades National Park. For total dissolved solid, under worst case scenario here also, I didn't mean to scare you, but it's really informative to see how the change in total dissolved solids would look like by the end of the century. As you can see, most places will have TDS and groundwater level more than 18,000 milligram of total dissolved solids per liter of water. And in fact, by 2090s, pretty much all areas in Miami will be highly contaminated with total dissolved solid. And based on literature, a rough rule of thumb for TDS and salinity is 1.52 times higher than salinity, which means if you divide this number by 2, you get the salinity level roughly in this water. So no question about it. We are living with it. We are experiencing it, and the projections from NOAA and our model simulation shows water level will increase, salinity, TDS will increase. So we were interested to study this a little bit in detail by conducting experiment in the greenhouse and combining that with model simulations again using funding from USDA. We have been doing this project for more than 4 years now. We are wrapping it up. What we wanted to do here is just to look into like what does that salinity and flooding mean to soil health in general, looking at different parameters, soil hydrological parameters, physical parameters, chemical properties, and biological properties, and looked at different management strategies as well. Not only we were interested to quantify and understand the negative impacts, but also we were trying to test different mitigation strategies that could be used at the field and different scales, smaller scale in fact, to reduce these negative impacts. And we were focusing on soil amendments. This is our experimental setup. As I was saying, we did this project, the first phase in a greenhouse by conducting some flooding studies. We used some PVC columns with different kind of sensors. So what we did was we bring seawater from the ocean and then groundwater from our farm, and we flood 2 different kind of soils, calcareous soils called chrome soil, the one I just described, and we have another type of calcareous soil called biscayne. We expose these 2 soils for different flooding durations, ranging from 1 day all the way to 28 days. And as I was saying, we had also kind of a control that we flooded the soils using relatively fresh water from groundwater, and that helped us to see the impact of salinity, not only flooding from seawater. We collected several soil moisture, temperature, salinity parameters using sensors. We collected pore water samples. I don't know if you can see pore water samples for water quality analysis. And also we collected greenhouse gas flux, different time intervals. This is a summary of data we have been compiling just to see the general characteristics of seawater. So since this project was ongoing for more than 4 years, we had to do the experiment across multiple years, and salinity fluctuation in the ocean was one issue. For that reason, we always tend to do it during the summer when salinity was peak between 40,000 and 60,000 in terms of electrical conductivity. Other elements in ocean water ranged 300 to 500 parts per million for calcium. Potassium is there. Of course, we expect sodium up to 12,000. magnesium up to 1400. There was a little bit ammonium nitrogen and nitrate nitrogen, and a little bit of phosphorus and total phosphorus. pH in the water pH from the ocean was more than 7. So this is our pore water quality results after the flooding experiment. So what happens when you expose these two different soils for different durations, and then different water types, freshwater and seawater? As you can see, there was a clear difference between the two soils. The chrome soil responded a little bit less than the Biscayne soil in terms of ammonium, nitrogen, phosphorus, and total phosphorus leaching or um, release. Uh, for Biscayne soil, as time goes on, which means as the flooding duration was extended, the release of these three elements, which are really the major elements, and if you look at in terms of water pollution, they, especially phosphorus, they tend to increase from Biscayne soil. And that was the case for chrome soil as well, but the amount of increase compared to Biscayne soil was not that big. For other elements, like mostly cations, including sodium, calcium, potassium, and magnesium, again, fresh seawater resulted in um, more of these elements in pore water compared to freshwater flooding. And for some of these, they tend to increase and level off after 1 day flooding, most of them. We also looked at, like, after flooding, how soil properties change. So we have baseline information, which means soil samples from before flooding, and then samples after flooding. And it was interesting both for Biscayne and chrome soils, pH reduced significantly. In most cases, like it was below 7 after 1 day of flooding. Other elements, copper, iron, manganese, magnesium, they increased. There were a few others, they slightly decreased and then stayed the same, like calcium, for example, it was peak and slightly decreased. And we believe there is, I'm not a biogeochemist or a chemist, but there is a lot of cation exchange and a lot of chemistry going on, and we are trying to understand that further by digging the data and involving other people who have experts in this data. Some results from greenhouse gas flex also. It was interesting, like here on the left side, you see nitrous oxide emission, where you see a significant drop, a peak flux on 1 day after flooding, and then a sharp decline afterwards. The same was true for carbon dioxide, especially for the Biscayne soil. A little bit of flux on day 1 and then a decline afterwards. Interestingly, methane was below detection limit. Initially, we were expecting that, since it's a saturated condition, a flooding experiment, we were expecting there will be some methane emission in there, but unfortunately, our data was consistent, and methane was below the detection limit. So if you add all this, it's not the groundwater level, sea level, but then once the soils are flooded, especially with high salt concentration, you've seen the different kind of elements being more soluble, and with implication for water quality. And it's important that we need to manage and come up with some management strategies. And the first one for salt is, if topography again is not an issue, and if freshwater availability is not an issue, and if there is enough depth between the groundwater and the unsaturated bone flushing, salt using freshwater could be an effective technique. And we tried to um, do that by simulating a flashing experiment in a greenhouse for the two soils we studied. The first, the chrome soil, after flooding, salinity spiked, and after flashing, it went back down where it was about 200 parts per million. For biscuit soil, after applying the same amount of water, which was about 1.5 gallon of water on 24-inch depth, and I believe 6-inch diameter PVC column, which is equivalent to 12.3 inches of rainfall. Still, it was not enough to unleash the salt from the skin soil. So different soils have different soil water properties, characteristics, and different water tension and cation exchange, which means the requirement for flushing salt, the total freshwater requirement is different. Of course, in this case, the skin soil would need more water. In collaboration with another faculty who was a co-PI, currently she's at Georgia Tech. We developed a hydrogel from sugarcane bagasse. There was some processes, lab processes, and chemical processes going on, which I'm not an expert, but at the end we will produce hydrogel, which is similar to this one in this picture. And it has some exciting, interesting features. First of all, it does not degrade. We did some degradation study in a greenhouse in the field, and after 6 months, we didn't see any structural degradation. And this material shrinks when it's dry and expands when it's moist. And its average water holding capacity was nearly 400% between the dry and the fully saturated condition. And once we apply this material in soil at different salinity levels, this is a study in the lab, again at different salinity levels, you can see with increase in addition of hydrogel, which is in terms of percentage from 1 to 3%, salinity, electrical conductivity decreased at 2 levels. This is a 5 dcm per meter solution. This is a 10 dcm per meter. Pretty much other elements were also decreased. One drawback was addition of hydrogel increased ammonium nitrogen. That's the only drawback. Another obvious management strategy that could help in promoting sustainability of freshwater resources and our reliance on groundwater, and hopefully reduce saltwater intrusion, is improving our ag water management at different scales. We had another project funded through NIFA. Again, we are wrapping up this project also. In this project, we were doing some precision irrigation study on 1 acre field that we established for sweet corn and green beans. I don't know if you can see the pictures in the field. We have the different kind of sensors, soil moisture sensors, infrared sensors. This irrigation system is equipped with VRI, variable rate irrigation technology, which basically allows you applying different rates based on a prescription map, similar to a GIS map that we developed and upload, and the machine applies based on that map. So we had sweet corn and green beans for 4 years. This is the how the VRI technology works. You develop the prescription map using a software and upload it, and it has a 4G connectivity. But a little bit about irrigation. Technology is one thing, which is nice, including the variable technology I mentioned, but you need to rely on data. The machine does what humans tell the machine to do. And in this case, we need some data to come up with a very efficient irrigation scheduling strategy that allows us to provide what plants need and what soils can hold. And that approach could be based on weather, We monitor the weather, calculate reference evapotranspiration, combine that with crop coefficient, and estimate the amount of water that has been lost through evapotranspiration. And we use that as information to develop irrigation scheme. The other could be monitoring the plants themselves. Plants respond differently under different moisture stress conditions, and um, we can use stomatal conductance measurement, leaf water potential, stem water potential, subflow meters, and canopy temperature as well. The other technique is, instead of monitoring plants and monitoring the weather, why not monitor the soil itself? Because the water we apply need to be stored in the soil and available for plants. And if we monitor the available soil moisture status, and we can use that information for irrigation scheme. Regardless where you are and the path you follow or the approach you follow, the end goal here is to provide what plants need. If you apply more, that means it's waste. We're not promoting efficient irrigation scheduling techniques. And for this study, we were doing our irrigation scheduling based on soil moisture. We monitor soil moisture using the soil moisture sensors, and we had 4 treatments. One 75 deficit all the way to 100%. So the 100%, if the 100% treatment gets 1 inch, the one if the 25% gets quarter an inch, which means a 75% reduction. So we applied these treatments for the 2 crops for several seasons, almost 4 years. And we have been collecting data, as I mentioned before, different kind of data. Uh, Using UAV systems and drainage lysimeters and other tools. So this is some results in terms of yield, because whatever practice or irrigation scheduling technique we propose or recommend, growers need to accept it. And the first thing for growers is the bottom line is yield, right? So interestingly, our yield results were consistent across 2 seasons here. The results is based on 2 seasons. Statistically speaking, between the 4 irrigation treatments we tested, there was no difference. For there could be slight difference if you look at the absolute numbers, but statistically speaking, they were not statistically different. But again, between the 4 treatments we tested in this study, which is a good thing from water conservation point of view, from cost reduction point of view, because growers use pump and manpower and others to run their systems to apply this to irrigate fields. And that was a good opportunity to save water. And water saving from green bean plots was up to 1,500 meter cube per hectare. For sweet corn, since it has a longer growth period up to 3 months, the water conservation or reduction from the 25% irrigated treatment was nearly 1,900 meter cube per hectare. So yeah, data, as I mentioned before, is critical. And the good data you give to the system and rely on to make a decision, the results or the output could be also reliable. And the challenge is how often can you measure data? Manual measurement, you could shift to sensors and other techniques, but even sensors, they have their own limitations. So in this regard, model simulation could be handy, because based on some inputs, if you can reliably simulate some output, in this case soil moisture, that could be much useful and fast. So based on the data we use, we evaluated one crop model, the DSAT model, another crop / hydrologic model, field scale, farm scale model, the Apex, and then the hydrologic model, the Hydrus one. The previous slide I showed for soil moisture was the 3 models were for soil moisture, but For evapotranspiration, we only were able to run DSAT and Apex. We're still working to run Hydrous 1D for ET, and they have different approach of estimating evapotranspiration, as you can see in this slide. So we have different sensors. Again, it's a repetition of what I said in the last two slides, but here I would like to point out they have already published two papers based on this work in computer and electronics in agriculture, and one is currently under review. So when it comes to ET, really the models, the DSAT and the Apex models they did not do good. They had lower performance in terms of R squared, index of agreement, and mean absolute error. The machine learning models were better. I didn't highlight the machine learning model, but we also incorporated machine learning models in addition to those two models in simulating soil moisture and ET. In this case, we have a light gradient boosting model, extreme gradient boosting model, and support vector emission model. The issue, regardless of the R square and error difference, was models uncertainty. Sometimes you hear in the x-axis that's observed ET, in the y-axis is model simulated for the different approach. You see for a single observed data, one here, for example, DSAT, estimates a range of values between 1 to 3.5 millimeter per day, while the observed was 2.5. This is we're trying to investigate what the issue is. If this is um, some model boundary condition, or we'll do some parameter sensitivity, because we're not replicating the same output for the same input. Shifting gears a little bit, because nutrient and water management go hand in hand. Water obviously is a vehicle to transport nutrients, chemical, and other farm inputs. 2 years ago or so, we were added to the team, the statewide team that's working to revamp nutrient recommendations throughout Florida. This was funding came through the legislature, FDACS, and then IFAS is coordinating this. And we were tasked to work on phosphorus specifically, and green beans, and the calcareous soil, chrome soil I just mentioned earlier. So the issue with phosphorus is that unlike nitrogen, it tends to stay in the soil in different forms. And if you test background soil phosphorus level, variation from field to field is very high. We sample more than 180 samples from, I think, 4 or 5 fields, and more than 180 samples. You see the range as low as like the 30s parts per million all the way to 500 parts per million. The current guideline, the IFAS guideline, is that for vegetables, if the background soil phosphorus level is 45 parts per million or more, you don't need to apply phosphorus. But growers don't agree with that, because they think that regardless of the background soil phosphorus level, they need to add phosphorus to get better yield. So developing PMPs for this soil was our task, and looking into economic, environmental, and agricultural productivity. And we have been doing this for now 3 years, and we hope we will wrap it up next year and make some recommendations for this specific soil as it relates to snapping production. Every time we do some research, we tend to leverage and collect more data. Even though this was purely a nutrient and irrigation management research, we have been collecting other soil, plant, water data using some of the tools we have in our. So based on trials we did on a commercial field and on a research plot at the Tropical Research Center, we preliminary findings showed that 129 pounds per acre is the maximum that we could apply in terms of phosphorus fertilizer for snapping production. Beyond that, there is no added benefit. We had two irrigation treatments in this study as well. One grower based tend to be higher, another based on evapotranspiration data. And between these two, we tested, we didn't see a difference, which was also consistent with our USDA project. So the current recommendation we came up with was 129 pounds per acre. But it has a catch. So if you look at this table, this is the estimate from the fields that we worked on, the average yield that farmers could get if they don't apply phosphorus. That's without the phosphorus. And plugging this equation based on, it's a quadratic relationship, yield response to phosphorus rate, and plugging this P rate and a P rate square for the first field, for example, here, that's you would get up to 129 pounds per acre, which is a little bit more than 9,000. But the catch is for every 10 pound additional phosphorus that growers add, their rate of return in terms of yield is diminished. Here, if they apply 10 pounds, this after zero, if they apply 10 pounds, they get one per acre, they get 149 pound snapping. The next 10 pound gives them 137, and eventually 120 pound gives them only, the last 10 pound gives them only 17 pounds per acre snapping. And the question is, it will become more of economics, like cost benefit analysis. And we are trying to collaborate on that with an economist. The phosphorus, we added the different rates, increased concentration in tissue only for in a few instances in 2022 and 2023 studies on research plots, but in most of the case, no change in tissue, which is the green beans leaf tissue samples. Concentration did not change that much, but in soil, they tend to increase, which is expected. So if there's excess phosphorus that we added that was not used by plants, eventually some might have been dished out. Some obviously should stay in the soil, and that's the case that we have been observing, even though the rate of increase was different across season and across. I briefly mentioned the two irrigation treatments we studied in this project. You can call them high and low. Growers is a little bit higher, 80 based is more based on data, it's a little bit lower. Even though there was no statistically significant difference in terms of yield, we observed some differences in terms of water quality. This is our result for nutrient leaching based on samples we collected in the root zone. And as you can see, between these two for phosphorus, the ET based resulted low phosphorus concentration in leachate water. The same thing for nitrate. The x-axis is different sampling dates. In the season, the same 2022, 2023 for both phosphorus and nitrate. So a few summary points: flooding and salinity are a big risk, and there's even a big question whether ag will be viable in 20 years, 25 years, 50 years in Miami and South Florida. That's a big question. It's probably $1 million question, but based on work that we have been doing and the model simulations, it's a big challenge. It's going. Water quality is another factor, not only the flooding of the soils, but also the high salt triggering phosphorus and ammonium and the leaching of other elements. And soil and water management practices would be beneficial. Of course, they show to be beneficial in terms of relying on data, promoting water conservation strategies. Uh, but the issue with BMP synthetic technology, um, it's adoption. Like current study shows that ag is lagging behind in adopting technologies, and I think the estimate is about 10%. So it doesn't matter whether if we have cutting edge, very impactful and, technologies that could literally significantly reduce water consumption and improve water quality, unless they are used by end users, growers, and other end users for the bigger change. With that, I will stop here and take some questions.
All right. Thank you, Jaime. Okay, so we'll take some questions from the room and see if we have any from YouTube as well. So I know there's a lot of different studies, a lot of different variables, a lot of y-axes and approaches. So what were you able to take from this? And maybe what was your biggest question for Dr. Biavio? Giving you a challenge on the last day of seminar. I may just wait a second. They take a little moment to percolate.
Yeah, I'm gonna do this one.
Go ahead,
I
AJ.
have a question, it's a little bit like more specific about the hydrogels. Actually, the moment you said it, I looked it up, because I didn't even think you were telling the truth. I was like, what is a hydrogel? And that seems really interesting. And then as I was looking, just like briefly, it seemed like there's like some pros and cons to using hydrogel, but they didn't have any like specific instructions on how people use them. So can you just like briefly talk about how people are using hydrogels in agriculture? Like, is it like going between the soil that's already there and they like, are they placing it above that soil to retain the water like higher up in the column? I don't know. I guess I'm not trying to conceptualize.
Yeah, how do you
How is it used?
physically employ the hydrogel? How is it used?
Well, if I understand the question correctly, as of now, as far as I'm concerned, I don't think it's widely used. I don't think it's growers or farmers use hydrogel and like they do manure and others. But for this project, we were interested to explore its potential in a lab and in a smaller scale, column scale study. That's what your question is how it's made and how I can talk
Yeah,
about
that answered it. Like if you're not using it, I guess on mass scale, then
Yeah.
it's still like preliminary type of things. That's all I wanted to know, like how.
Yeah, I think that's a good question. But the issue is its production is also tedious. It takes time. It involves a lot of chemical reaction, chemicals, and it takes a lot to produce it. But the good thing is we were able to produce it using a waste sugarcane bagasse. Um, but scaling it up and thinking about field scale application, no, it needs more work, more efficient production systems, cost reduction also to produce it. But it was interesting because we found it like it's never breaks, never degrades, and we thought if we find a way to produce it and in an efficient way, and it could be applied in soil and could be there for at least several years, at least a couple of years, if not several. Yeah.
You said it doesn't degrade. Is that a good thing though? Like, don't you want it to kind of like over years? I guess not decompose, but that be decomposing.
Yeah, I mean, you could say degrade, decompose. Yeah, you are right. Uh, you might want some materials to decompose, right? If talking about plastics and other waste, but for soil amendments, like biochar, for example, You want them, you apply them, especially if they are organic amendments and no known negative impacts. If you want their benefit to long last, because you tend to apply them in bulk, and applying those kind of materials every year or every other year may not be feasible. You want them to last longer. Biochar, for example, people say it could stay in soil for several, I don't know, I don't want to misquote, but more than some in 100 years range. So, and that's a good thing, because for carbon sequestration, improving soil health, improving soil water relationship, that's good with benefit. And for hydrogen, the same thing. Looking at the benefits, you want the hydrogen to stay in the soil and stay there longer, so that you don't have to apply it every year.
Yeah, so let's zoom out a little bit. Any more like larger scale questions for Dr. Bayabil? Yeah, Maya.
You probably don't actually like have an answer for this. This is just like a conceptual like thinking. But I was wondering, would it make more sense to start to abandon Miami now than to plan to put in all of this time and money in the future trying to continue agriculture there if it will take so much work and money?
There you go.
I think that's a very sensitive question, because it's sometimes ag is more than money, it's more than people's livelihood. And I don't think that's a simple question we can easily say, oh, it's just, let's relocate, let's build here, let's build there, and like abandon. As you said, I don't have the right answer, but I don't think it's also kind of right way to frame the question. And I think we need to find a way to make living and farming in South Florida sustainable than taking the 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 easiest route or the exit. Yeah.
Thanks, Jaime. So yeah, I think for all of us to think about all of these questions and sea level rise and marsh retreat and mangrove advancement and cities becoming inundated and agricultural lands, right? And so there's going to be an evolution. It's, you know, and at some point there will be abandonment. There has been already in many places around the world, you know, cropland and residential land and, you know, homeland abandonment based on climate, not just sea level rise, but other things like changes in temperature and precipitation. And so to expect that that won't happen is probably ludicrous, but to plan for it in a way that maintains sort of livelihoods and social cultural fabric along the way out is probably is what's going to happen. And so being able to plan for managed retreat in a way that doesn't lead to abrupt collapse is probably something we should be thinking about in many contexts, from agriculture to cities to politics to everything. So maybe with that, we'll end the semester, and we'll thank Dr. Bayabil again for joining us. So thank you.
Thanks.
And so I don't know how you're doing. I'm only 1 week behind on my abstract grading.
I'm caught up now.
Oh, you're caught up? Okay, so we'll get those graded and please.
I'm good, David. I can leave, or you want me to stay?
What's that?
You want me to stay, or?
Oh, you can go.
You're good. Thank you.
Jaime, we'll talk
All
to you
right.
soon.
Bye. Have a good day. All right. Bye.